Okay, this is a lecture that I'm putting together on Einstein's special theory of relativity. I make it accessible to as many people as possible, so for the most part I'm not going to do too much math. I'm going to try to focus on the concepts. At the end of the lecture I'm going to put up some videos where I solve some problems, because example problems are a very important tool for teaching physics. The examples that I'm going to be discussing come from this book. This is a book called Relativity, written by Albert Einstein. It was written in 1916, and most of the introductory textbooks basically take the examples from that, and there's only going to be a few examples that I'm going to focus on, and they came out of Einstein's book that he wrote. And understanding those examples, having a conceptual understanding of those examples, will make learning the theory of relativity much easier, and it will just open the floodgate to learning the math. Okay, so what I'm going to be discussing is Einstein's special theory of relativity, and it's called the special theory of relativity because there are two theories. There's his special theory and his general theory, and so the special theory, the word special, is to differentiate it from the general theory, not because the theory is so special, although the theory is special. So Einstein came up with two postulates for his theory of relativity, and I'm going to read through the postulates and then explain them. So the first postulate is that the speed of light is the same when measured by any observer, and the background of where these postulates came from I'm not going to get into. That's beyond the scope of this lecture, and in order to understand relativity you don't actually need to know the history. To be a well-rounded physicist you obviously do need to understand it, and it came from Maxwell's equations and showing that light is an electromagnetic wave that travels with a certain speed. But understanding all that really doesn't help to understand relativity. And once he wrote down his first postulate, he took that and the second postulate to form the theory of relativity, and so you don't need to understand how he came up with the postulates in order to understand relativity. So that's the second postulate is that the laws of physics are the same in any inertial reference frame. Again, I'm going to come back and explain these two postulates, so I'll explain what an inertial reference frame is. Another way to say the second postulate that I feel is easier to visualize and easier to understand is that any observer in an inertial reference frame says that they are at rest and objects around them are moving relative to them. No experiment can be done to show absolute motion. So let's discuss these two postulates. So first of all, the speed of light is the same when measured by any observer. So imagine that I have, well, you don't have to imagine, I have a tennis ball right here, and let's say that I throw it. So I'll throw it, and it hits the wall and comes back to me. Now when I threw this tennis ball, Einstein over here can measure how quickly it's going, and let's say that I throw it at 5 miles an hour with my incredible pitching arm, and he would measure that this tennis ball goes 5 miles an hour relative to me. Now let's say, imagine, now you do have to imagine that I'm in a car or a space shuttle. Let's make it a car actually, and I'm driving along here at 50 miles an hour, and then out of the window I throw the ball, and we're going to assume there's no air friction, okay? So we're going to have to do a lot of imagination here. There's no air, we're in a vacuum. I take out the ball and I throw it at 5 miles an hour, but I'm driving at 50 miles an hour. Now, how quickly does Einstein measure that I throw the ball? Well, I'm driving 50 miles an hour and I throw the ball 5 miles an hour relative to me. So Einstein says he would measure that I threw the ball at 55 miles an hour relative to him. The speed of the car plus the speed that I threw the ball. Now let's imagine that I have a flashlight, and I guess you'll have to imagine this, and I take the flashlight and I turn it on. And the light starts propagating forward, photons start coming out, and Einstein measures the speed of light, and what he would measure is that it's 3 times 10 to the 8th meters per second, which is the speed of light. Now imagine that I'm driving in a space shuttle and I'm going very quickly. I don't have to be going very quickly, but it makes it a little more exciting. And I'm going 5,000 miles an hour, and then I turn on the headlights. Now, how quickly would Einstein measure that the light that comes from the headlights? Well, it's logical to say that he would measure it at the 5,000 miles an hour of the car plus the speed of light, adding the speed of the car, the speed of the space shuttle to the speed of light, just like we added the speed of the car to the speed of the tennis ball. But in fact, that's not the case. He would measure that the speed of light is the same, because that's the first postulate of relativity, and that's the way that the world works. And so he would measure that the speed of light is 3 times 10 to the 8th meters per second. And studying relativity, you need to know how he wrote down these postulates. You just need to understand the postulates, and then those postulates are used to form the theory of relativity. And so now let's talk about the second postulate of relativity. Okay, so now I'm going to talk about the second postulate and explain it. So the second postulate of Einstein's theory of relativity says that the laws of physics are the same in any inertial reference frame. And so first of all, what is an inertial reference frame? Well, the best way to think about it is imagine that there's a large ship or a large planet or something in space that is moving without any sort of acceleration. So if you're in space, you're far away from gravitational fields, you're deep in the middle of space where there's no planets, there's no stars, you're in some location of space, and there's a ship, or maybe there's three ships. Let's assume that there's three ships or three big asteroids. There's these objects, and they may be moving relative to each other, or they may be at rest relative to each other, and this is what you should think of as an inertial reference frame. It's better to think of something in space when you start thinking of things on Earth, like a car moving, or there's just a lot of forces on Earth that can lead you astray and make it so it's more difficult to understand the theory. So an inertial reference frame, what we're going to think of, an inertial reference frame is going to be a very large spaceship in space moving without any acceleration. There's no, or not even moving, with no acceleration. There's no gravity, there's no thrust, there's no engine. It's just this ship in space, and that's what an inertial reference frame is. It's something that's at rest or in relative motion, and it is not accelerating, and that's just the way that we're going to discuss an inertial reference frame. Now, Einstein's second postulate says an observer in an inertial reference frame says that they are at rest and objects are moving relative to them. There's no experiment that for absolute motion. So let's assume that there's three ships. Bob is on one, Mike is on another, and Jenny is on another. Now, in Bob's inertial reference frame, Bob is not moving. That's what Einstein's second postulate says. Bob says he's at rest and everything around him is moving relative to him, and there's no experiment that can show otherwise. So Bob is on his ship and he sees Mike fly by him at 70 miles per hour, or Mike moving relative to him. It doesn't have to be flying by him, Mike could be over here, but Mike is moving at 70 miles an hour relative to Bob. And Jenny is on another ship, and Bob sees Jenny moving at 10 miles an hour relative to him. Well, now let's take a look at Mike's reference frame. So if we're in Mike's inertial reference frame, Einstein's theory of relativity, the second postulate, says Mike says he's at rest and everything is moving relative to him, and there's no way that there's no way Mike could ever do any sort of experiment that says that he's moving. So what does Mike see from his reference frame? Well, Mike is at rest. He's not moving. He looks at Bob, and Mike sees that Bob is moving at negative 70 miles an hour relative to him. And then Mike looks at Jenny, and Mike sees that Jenny is moving at negative 60 miles an hour relative to him. So from Bob's inertial reference frame, he's at rest. He sees Mike moving at 70 miles an hour and Jenny moving at 10 miles an hour. Now from Mike's inertial reference frame, he says that he's at rest and there's no experiment or no physics that he can do to show that he's not at rest, which means every test and every experiment that he does in his inertial reference frame says that he's at rest, so he is at rest. That's just what it is. He's at rest and he sees Bob moving at negative 70 miles an hour relative to him and Jenny moving at negative 60 miles an hour relative to him. Now let's take a look at Jenny's inertial reference frame. Well, Jenny says that she's at rest. Every experiment that she does confirms that she's at rest, and she would see that, let's see what Jenny sees. So Jenny is, Jenny's at rest, so she's going to see that Mike is moving forward at 60 miles an hour, and she is going to see that Bob's moving backwards at negative 10 miles per hour relative to her. And so this is the second postulate of relativity. This is how you should think about the second postulate. And this is how you should think of an inertial reference frame. So whenever you're first beginning out with Einstein's theory of relativity, these are the examples that you should be thinking about in your head. You should be thinking about ships moving through space that are not accelerating. And so this is how you should think about it. And everybody on their own ship, they're not moving. They say that they're not moving and everything around them is moving, and there's no physics, there's no experiment, there's nothing that anyone could do on their ship to show that they are moving. and so they're not moving. And so this is how you have to think about relativity, and this is Einstein's second postulate of relativity, and combined with his first postulate of relativity, the whole theory of special relativity comes out from these two postulates. Okay, so now that I've discussed what the postulates of relativity are, I want to tell you what the special theory of relativity is. So Einstein used his great intuition, and he took the postulates of relativity and he put them together to come up with equations of motion that agree with the postulates of relativity. So what I want to do now is tell you what the theory of relativity is. I've broken it up into 4 points. I'm not going to explain it right this second. I'm going to tell you what it is, and then just lay it out there for you, and then come back and carefully explain each one of the points as they agree with the postulate. So imagine, again, that there's an inertial reference frame A. Let's say that we're in that inertial reference frame A, which means we're not moving. That's the second postulate of relativity. We're far out in space. There's no gravitational forces acting, no fields, no friction, and we're on spaceship A, not moving. Spaceship B is moving relative to spaceship A, so we're standing here, we see spaceship B flying relative to us. Well, so Einstein's special theory of relativity says 4 things. The first thing says that observer A, which is us, we measure time on the moving spaceship to run slower than our time. So you can think about this. Let's say that right now I'm in a spaceship, and there's a window on my spaceship right here, and I have binoculars. And then spaceship B flies by, and there's a window on spaceship B, and it has a clock in that window. There's just a clock in that window. I look out with my binoculars, and I look at that clock, and I watch that clock with my binoculars, and I watch it for 10 minutes, until 10 minutes has passed on that clock. If I look at the clock in my own spaceship, more than 10 minutes has passed, because when objects move relative to something else, time slows down for them, and this is called time dilation. And again, I'm just telling you what special relativity is. I'm going to explain it in a few minutes, but first I just want to lay it out there for you and tell you what it is. So when an object is moving relative to another object, its time slows down. Another part of relativity is called length contraction. And so when an object moves, so again, I'm in my inertial reference frame, spaceship A, and if spaceship B flies by me, spaceship B will shrink in the direction of motion. It will be shorter than, I will see spaceship B to be shorter than I would see spaceship B if it were not moving. This is called length contraction. When things move relative to something else, all motion is relative, so it depends on the observer. But if I'm here and I see something moving relative to me, it will shrink in the direction of motion, and this is called length contraction. Another part of relativity is that events that are simultaneous in one inertial reference frame are not simultaneous in another. And I'm going to come back and explain this next. And then finally, when an object moves close to the speed of light, it gets harder to speed it up. So you can think of this as when an object starts moving close to the speed of light, its mass increases. There's a formula, m is equal to m naught, which is rest mass, times gamma, which is 1 over 1 to the square root of 1 minus beta squared. But you have to be careful, because its mass doesn't actually increase in the sense that its gravitational field doesn't increase. So if an object is going the speed of light, it's not going to turn into a black hole. Or if an object gets going close to the speed of light, its gravitational force does not increase. But it does become harder to change its motion. So if I put a force on an object that's not moving, and then if I put a force on the same exact object that's moving close to the speed of light, it will accelerate less when it's moving close to the speed of light, which is kind of like its mass increasing. It's similar in some ways to its mass increasing. And finally, so this is relativity. So what is Einstein's special theory of relativity? This is Einstein's special theory of relativity. And I have one more note that I want to make, and that's relativity is all about light signals being transmitted between different inertial reference frames. So the whole theory is all about light signals being transferred back and forth between different inertial reference frames. And I'm just going to be discussing light as like a flashlight, as visible light. But I assume you know, or if you don't know, you should know that light is any sort of electromagnetic radiation, and it doesn't just have to be visible light. It's not just visible light. But for this lecture, let's just discuss visible light, because it's going to make everything a little bit easier. Okay, so now what I'd like to do is discuss the relativity of simultaneity. And so I'm going to discuss and explain the statement that events that are simultaneous in one inertial reference frame are not simultaneous in another. Relativity only works when you're dealing with light or things going close to the speed of light. So let's first take a look at a classical example. And I don't want you to get too confused, because in this example, things are simultaneous. Events that are simultaneous in one frame are simultaneous in another. But this is a classical example, and then I'm going to move on to an example where we're dealing with light and things moving the speed of light, and then you'll see that things are not simultaneous. But I first want to discuss an example where things are simultaneous, because this is Newtonian relativity, not special relativity. So we're going to look at an example where things are simultaneous, and then an example where they're not simultaneous. So imagine that there's we'll say that there's a train right now, because it's not relativistic. We're not discussing special relativity, but Newtonian relativity. So we could have a train moving on a train track on Earth. Although it's always better to imagine a spaceship moving in outer space with no gravitational field and no friction, no forces. So you can obviously think of that in this case as well. So we have a train, and the train is going to be moving at 1 meters per second along a track. The train will be 20 meters long, and Mike, random guy Mike, is going to be standing right in the center of the train. Now Sally is standing outside on the train tracks, and we'll say that the train has a huge window. It's just the train is a show train with a massive window, and so Sally can look inside and see everything that Mike is doing. Now Mike, at time t equals 0, he's got an iPhone, and he sets his stopwatch to t equals 0 and hits start. And right when he hits start, he takes 2 baseballs and he simultaneously throws them, one to the right and one to the left. Well, so Mike throws 1 baseball at 5 meters per second relative to him to the right, and 1 at -5 meters per second relative to him to the left. And after 2 seconds, each one of these baseballs has to move a distance of 10 meters in Mike's inertial reference frame. And so after 2 seconds, the balls will simultaneously hit the 2 walls of the train. So if I'm standing here, I throw the balls, and I'm right in the center of the train. After 2 seconds, I will look, and the balls will hit the walls of the train at the same time, simultaneously. Now Sally, who is outside of the train, she also sees that the balls hit the 2 walls simultaneously. And the reason that she sees this is because Sally sees that the train is moving forward at 1 meter per second. And so when Mike throws a ball at 5 meters per second, Sally actually sees that Mike throws this ball at 6 meters per second, because it's the speed. This speed is the speed relative to Mike. And Sally sees the whole train is moving forward at 1 meter per second. So she'll see that Mike will throw the ball this way at 6 meters per second relative to her. It will be 5 meters per second relative to Mike, plus the motion of the train, which is 1 meter per second. And she'll see that this ball is thrown backwards at -4 meters per second. However, she still sees that the balls hit simultaneously because the train is moving, and so this ball has a farther distance to go before it hits the wall, because the wall's moving away from the balls. And this is from Sally's reference frame, from her inertial reference frame. Sally sees that this ball has a longer distance to go, and this ball has a shorter distance to go, but the ball on the left is moving slower than the ball on the right relative to Sally. And so even because it's moving slower and it has less distance to travel, and the one on the right is moving quicker but it has more distance to travel, it all works out that both balls hit simultaneously, both in Mike's inertial reference frame and also in Sally's inertial reference frame. Now I have another example, which is essentially the same example but in reverse, and I want to go over both because I think that it's informative to look at both these, especially once we get into light. Okay, so now another example is that it's the same train. Mike is still in the center of the train. Sally is still outside on the track watching through the big window on the train. The train is still moving at 1 meter per second relative to Sally. In Mike's inertial reference frame, he's at rest. And right now this is unimportant, but for Mike's inertial reference frame, Sally is moving -1 meter per second relative to him. And imagine that there's 2, we'll say they're like pitching machines or ball machines on both sides of the train. And at t equals 0 seconds, Mike hits some button, and it causes these balls to get shot at 5 meters per second towards him. Now, after 2 seconds, both the balls will hit Mike, or hopefully he'll catch them. And so after 2 seconds, simultaneously, both of the balls will end up right where Mike is. Now, from Sally's point of view, that is still the case. She still sees both the balls hit Mike simultaneously, but Sally sees that this ball here will move at 6 meters per second, to the right because it's the 5 meters per second plus the 1 meter per second. And then this ball is going to move at -4 meters per second. But Sally sees Mike moving. So Sally's going to see Mike move towards this ball. So this ball has a... Sally sees Mike, so the balls are moving, but Mike is also moving. So this ball has a shorter distance to travel before it hits Mike than this ball, because Mike is moving away from the ball coming this way, and Mike is moving towards the ball coming this way. And so, but Sally still sees that the balls hit Mike simultaneously, because the two balls, this one will be going slower, and this one will be going quicker, but this one has a longer distance to travel because Mike is moving away from it, and this one has a shorter distance to travel because Mike is moving toward it, and they both hit him simultaneously from both inertial reference frames. I'm going to discuss the same example, except we're going to replace the baseballs with light. So now Mike is going to be on a spaceship out in space with no forces or friction or air resistance or anything like that. And this spaceship's going to be moving at the speed of light over 2, just because that's what I've picked. And c is the universal symbol for the speed of light. It's named that because the Latin word for swiftness begins with a C. And so Mike is inside a space shuttle, Sally is standing outside of the space shuttle, Mike is moving relative to Sally, and Mike has 2 flashlights. He's holding the flashlights, and simultaneously he hits the flashlights, and photons come out, and he sends a pulse of light. Now, so Mike sends this pulse of light, 2 pulses of light, one going to the right and one going to the left relative to him. And after 2 seconds, Mike sees that the light hits the sides of his spaceship at the same time simultaneously. He's standing here, turns on his flashlights, click, and he watches, and the light hits both sides of the spaceship at the same time. It's a massive spaceship, obviously. Now, from Sally's point of view, the first postulate of relativity and the way that the world works is that every observer in any inertial reference frame has to measure the speed of light to be the same. So Sally sees that Mike turns on his 2 flashlights, and she sees that the speed of light is what the speed of light is, 3 times 10 to the 8th meters per second, but Sally's going to see that this wall is moving towards the light, and this side of the spaceship is moving away from the light. And so Sally will see the light hits this side first, and then this side. So in Mike's inertial reference frame, both light pulses hit the sides of the ship simultaneously at the same time. But in Sally's inertial reference frame, light hits this side first, and then this side, and that's the way she sees it, and that's the way it is in her reference frame. There's no experiment that shows that one person is right or one person is wrong. These are what people see from different inertial reference frames, and this is what relativity is all about. You can look at this, then we can look at the second example, which is just to really nail this point in. So now, same situation, Mike is inside his spaceship, and there are 2 light sources on both sides of the spaceship, and Mike has a little switch, and when he hits the switch, these lights will turn on and send a pulse of light, and that pulse of light will hit him. Now, in Mike's inertial reference frame, he's moving at c over 2 in this direction, so relative to Sally. He's moving at the speed of light divided by 2. There's a big window. Sally can see inside his spaceship. And so Mike sees, so Mike hits the button. The 2 light pulses come out from 1 and 2 simultaneously. And then at t equals 2 seconds, the light pulses hit Mike simultaneously. So we'll see the 2 pulses hit him simultaneously. Now, from Sally's point of view, the light pulses hit Mike simultaneously, but the only way that can happen is if light pulse 1 is shot before light pulse 2. So from Mike's point of view, both of the lights turn on simultaneously. From Sally's point of view, first 1 turns on and then 2 turns on because the light moves at the same speed, but Mike is moving away from 1, so 1 has to go a longer distance, and Mike is moving towards 2. And so this is the thought experiment, and this is the explanation for why events that are simultaneous in one frame of reference are not simultaneous in another inertial reference frame. Okay, so now I'm going to discuss time dilation. Recall that I broke relativity up into four things. Length contraction, time dilation, the relativity of simultaneity, and relativistic energy, E equals mc squared. So those four things constitute the special theory of relativity, and they came about because the two postulates of relativity, so now let's discuss time dilation. So time dilation says if Bob moves relative to Mike, Mike will see Bob's clocks run slower. So again, relativity is all about people making observations in different inertial reference frames. So I'm just picking examples, Bob and Mike. It could be you and me. If I'm moving relative to Albert Einstein, so if I'm moving relative to him, he's going to measure my time to slow down. So that's what time dilation is, and that's what we have here. Now, the example that Einstein came up with was a light clock, and this is covered heavily on the internet. You can look on the internet for examples of light clock and relativity, and there should be a lot of very nice animations there that show what's going on. But let's say that there's Mike, and Mike is at rest in his inertial reference frame. So he's right here, he's not moving, and he makes a light clock. And what a light clock is, it's two mirrors separated by a very large distance, and there could be a pulse of light. And the pulse of light will go from the bottom mirror to the top mirror and come back down. And in making one round trip, so there's a light down here, you turn on a pulse of light, it goes boom, boom. And when the light hits the top mirror and then reflects back down, and making one cycle, that's 1 unit of time. So Mike has his his light clock, and Mike can measure how much time it takes for 1 unit of time to pass. And he gets that C delta T0 is equal to 2L. This distance here is L. I guess I should write that. So the distance between the two mirrors is L. Velocity times time is equal to distance. C is the speed of the velocity of light. Velocity delta T0, this is the time it takes for light to go from the bottom to the top, back to the bottom, as Mike sees it on Mike's light clock. And so you get this formula. This delta T0, this is called the proper time. I think I should come back and explain what proper time is a little bit later. But right now, all you need to know is that Mike has his light clock, and delta T0 is the amount of time it takes for light to go from the bottom to the top, back to the bottom of Mike's light clock as measured by Mike, when Mike looks at it. So now, Bob is moving at some velocity relative to Mike. Bob is in a large spaceship with a window on it, so Mike can look inside the window and see Bob. Here's Mike at rest. Here's Bob, who's flying by Mike in a spaceship at some velocity v. Now, Bob also has a light clock inside of his spaceship. And as the light, and so what Mike sees that the light in Bob's light clock makes this triangular path. So Mike sees his own light just goes straight up and straight down in his light clock. But because Mike sees Bob moving relative to him, Mike will see that the light in Mike's light clock moves like this. So now, using some high school trigonometry, you can drop a perpendicular and make this into a right triangle. So this is the right triangle. And this portion of the triangle is L, which is the distance between the two light clocks. And L is equal to C delta T0 divided by 2. And then this bottom part of the triangle is the velocity that Bob is moving times delta T over 2. Delta T is the time for the light to go from the bottom mirror to the top mirror and back to the bottom. And delta T over 2 would be the time for it just to go from the bottom to the top. And we're doing delta T over 2 because we're just looking at that right triangle. And so, V delta T over 2 is this distance. And then velocity times time would be the hypotenuse. Velocity is the speed of light, because it's the speed of light is what's actually traveling there. And then the time is delta T over 2. And then you use Pythagorean theorem, and you say a squared plus b squared is equal to c squared. And you set this up, and what you get is delta t is equal to delta t0 divided by the square root of 1 minus beta squared. Beta is equal to v over c. And this is delta t is equal to gamma delta t0. Gamma is called the Lorentz factor. I have gamma plotted here as a function of velocity. Gamma is 1 at non-relativistic speeds, but once you get going close to the speed of light, Gamma blows up asymptotically to infinity. The formula says delta t equals gamma delta t0. In the case when gamma is equal to 2, then if delta t0 is 1 second, delta t is 2. So what does this mean? Well, delta t0 is the time Mike sees that it takes for light to go from the top of Mike's clock in his inertial reference frame, from the bottom of his clock to the top and back down. That's 1 second. That's delta t0. Delta t is the time that Mike sees for light on Bob's light clock to go from the bottom to the top, back to the bottom. 1 unit of time passes on Bob's clock. Mike will see 2 units of time pass on his clock. Mike says that Bob's clock is running slower than his. So delta t is the time for 1 unit of time to pass on Bob's clock, on the moving clock. This is the amount of time that passes on the moving clock as light goes from the bottom to the top, back to the bottom. Delta t0 is the amount of time that passes on the stationary clock, and this is all in Mike's inertial reference frame, as light goes from the bottom to the top, back to the bottom. Mike sees that Bob's clock passes time slower. It takes longer for 1 unit of time to pass on Bob's clock. It takes longer for 1 unit of time to pass on the moving clock than it does on the stationary clock in the reference frame of whoever's stationary, of course. And this is in Mike's reference frame. And so Mike sees that Bob's clock are running slowly. Well, what does this actually mean? So if I was moving very, very quickly near the speed of light and I was in a space shuttle, there was a window looking into my space shuttle, and I was flying by very quickly, and you could look in the window. You would actually you'd see the space shuttle zooming by, but in the window, you would see me moving in very, very slow motion, and if the spaceship was moving at the speed of light, I would be frozen, or however I would be at that point, and you would just see me frozen there, because when things go towards the speed of light, at the speed of light, time stops. So if I was with a group of people, if we were playing a football game, and the ship was going by at 87% of the speed of light, and you watched the football game through the window of the ship that flew by you, you would see everything happening at half speed. You'd see the ball moving through the air at half speed, and if the ship was going quicker, things would be going slower and slower, and so it would be like watching a movie or something in slow motion. That is through the window of a ship that was flying by you at a high speed. Length contraction. Length contraction is one of the 4 parts of relativity that I talked about. So let's read what length contraction is. Length contraction, the length of an object moving at relativistic speeds undergoes a contraction along the direction of motion. So if I'm at rest in my own inertial reference frame and somebody flies by me, I will see that they shrink in the direction of motion, and they shrink proportional to gamma, the gamma factor, the Lorentz factor, 1 divided by the square root of 1 minus beta squared. And so to give you some understanding of why this might be the case, I'm going to talk about how I would measure something which is moving by me. So I'm going to use 0. 0 is this character, so this is 0. Okay, so now I'm going to show you how to measure the length of an object who's moving relative to you. So I'm in my own inertial reference frame, and this whiteboard behind me is also in my own inertial reference frame. So it's at rest relative to me, and a spaceship can fly by in a different inertial reference frame, moving relative to me, and I want to measure the length of that spaceship. Well, what I do is when the spaceship passes me, I'm going to put a mark in my inertial reference frame at the front and the back of the spaceship simultaneously, and then I can measure the distance between those 2 marks. So I'm now going to measure a spaceship flying past me. So I'm in my inertial reference frame, and the spaceship's going to start coming out. And here's 0. Now when the spaceship comes out, spaceship's still moving. Use a little bit of imagination. I simultaneously, let me just do this. So when the spaceship flew by, I simultaneously marked the front and the back. Here, just hold this here for a second. Just hold it over here. You have to come here. as this was moving, I simultaneously at the same time marked the front and the back. This was moving now, this was moving. As it was moving, I simultaneously marked the front and the back of the spaceship. So now there are marks in my own inertial reference frame. And so now I say, well, how long was the spaceship that just flew by at relativistic speeds? Well, I have my own inertial reference frame, the marks here, and I measure the distance. I take out a ruler, and I measure the distance between those two marks, and I say that that spaceship was 1,000 feet long or whatever it was, and the person on the spaceship would say, no, I'm bigger than that, because if they measured themselves, they're moving relative to me, and because they're moving relative to me, they shrink in the direction of motion. So 0 flies by in the spaceship. Maybe I can see this. So 0 flies by in the spaceship, and I make marks. I make simultaneous marks. We're going to say that the marks are firecrackers. So firecrackers are going to go off, and they're going to mark the area, the location where they go off. But light from the firecracker, so as 0's traveling, I simultaneously set off a firecracker at the back and the front of his ship as he passes. Now the light from this firecracker is going to move towards him, and it's going to hit him, and the light from this firecracker is going to move towards him, and the speed of light is the same. Well, which light is going to hit 0 first? The light from the front firecracker or the light from the back firecracker? Well, as you notice, the light from the front will hit him first because he's moving towards the front and away from the back. And so even though I put these two marks simultaneously, they didn't hit 0 simultaneously because he was moving. So in his reference frame, he sees that the light hit him from the front first and then from the back. And in my inertial reference frame, I see that the light first hit him from the front but from the back. So we both agree on that. But we disagree on the reason why that is the case. I say the light hit him first from the front and then from the back because he was moving towards the light. He says, no, I'm in my own inertial reference frame, I'm at rest, but I do agree that the light hit me from the front first, then from the back, and the reason is, it's because you didn't put those two marks simultaneously. My ship was flying by, first you set off a firecracker at the front of the ship, and then you let the ship move forward a little bit. So the ship, here's 0. Now, from my point of view, from my inertial reference frame, he is flying by, and I simultaneously, at the exact same time, put these two explosions simultaneously. 0's having a problem, we're taking him off. Imagine he's still there. Simultaneously, I put these two marks here. And I say, first the firecracker from the right hits 0, and then the light from the firecracker from the left hits 0. From 0's inertial reference frame, he's at rest, and there's no physics, no experiment that he could ever do that says that he's not at rest, which means I must be moving backwards relative to him. But regardless, he's at rest. Now he's at rest, and he sees light hit him first from the front, and then from the back. So what in his reference frame, what he sees is that I did not put these two firecrackers, I did not explode them simultaneously, but instead what happened was his ship was coming through, and then I set off a firecracker at the front, and then a little bit later in time, he kept on moving, and then I set off a firecracker at the back. And obviously, I'm going to measure that his ship is shorter than he measures it to be, because I did not set off both firecrackers simultaneously. However, events that are simultaneous in one inertial reference frame are not simultaneous in the other, and so everything is consistent, but this is an explanation to try to help you understand why length contraction is what it is, and why when objects move quickly close to the speed of light, an observer who is not moving relative to them will see them shrink in the direction of motion.
Okay.
So relativistic energy is one of the most practical aspects of relativity. It's part of relativity that has many applications and uses that come up in technology. So when the speed of light is the speed limit of the universe, you can't go quicker than the speed of light. One hand-wavy argument for relativistic energy is if you have an object and it's getting very close to the speed of light, if you keep putting a force on it, force equals mass times acceleration, then you'll accelerate it and keep speeding it up until its speed becomes greater than that, than the speed of light, which violates Einstein's relativity. You can't go quicker than the speed of light. So when things get close to the speed of light, if you put as you put force on them, they become harder and harder to speed up, which is kind of like saying that their mass increases, except for the gravitational effects don't increase. Relativistic energy is something I really need to come back and give a lot more, a full lecture on, which maybe I'll do. But the equations for relativistic energy are E equals gamma m naught c squared, and then E squared equals p squared c squared plus m naught squared c to the fourth. So this is relativistic energy. Kinetic energy is gamma minus 1 m naught c squared. And gamma, if you remember, is 1 over the square root of 1 minus v squared over c squared. And yeah, gamma is 1 minus v squared over c squared. You can write gamma as 1 minus beta squared, beta is v over c to the minus 1/2. And Taylor expand this, or use the binomial expansion. And so then you get gamma is equal to 1 plus 1/2 beta squared. And you take this gamma and you plug this back in here and you get 1/2 mv squared. So relativistic energy turns into, relativistic kinetic energy, this is the correct formula for kinetic energy at any speed. And at speeds that happen in our everyday life, of speeds that humans are used to and accustomed to, kinetic energy is 1/2 mv squared. And the formula for relativistic energy turns into the formula for non-relativistic Newtonian kinetic energy when the speeds get closer to human speeds, speeds that humans are accustomed to, and farther away from relativistic speeds.